A particle is going around a circular path in the xy plane with the origin as the center of the circle. The red vector is the linear momentum vector and the blue vector is the position vector of the particle related to the center. Their cross product is along the z-axis shown in black. It is that black vector represents the angular momentum of the particle about the center. Though the linear momentum vector and the position vector are changing, their cross product remains same. Its constant magnitude because V is not changing. It's moving steadily. The particle is going around the circle steadily. And it's nice that a steady circular motion is represented by a constant vector. We are now interested in angular momentum of this particle about a point at some height above the center. The blue vector, which is the position vector of the particle related to the point on the axis, is of length root of r squared plus h squared, where h is the height of the point above the center. The angular momentum vector is shown in black and is now inclined to the z-axis. You can see the plane of position vector and the linear momentum vector, and the angular momentum vector is perpendicular to this plane. This is the plane containing angular momentum vector and the position vector, and you can see the linear momentum vector is at right angles to it. The angular momentum vector can be split into two components, parallel to the axis and perpendicular to the axis. The green vector can be shown to be equal to mvr, that is, the component along the axis not changed due to the change in height of the point above the center. The component perpendicular to the axis shown in pink is mvh, and this is a variable vector. It's varying in direction. Its magnitude is unchanged because it's a steady circular motion. If there were a paired particle diametrically opposite, moving in the same sense, the component of the angular momentum of that particle perpendicular to the axis would have cancelled out the component perpendicular to the axis of the first particle. The components parallel to the axis would have added up, and it would have been mvr plus mvr 2 mvr. Or if you replace V with r omega, it will be mr squared omega plus mr squared omega, that is 2 mr squared omega. If there were many such paired particles going around circular path, the angular momentum components perpendicular to the axis cancel out, and angular momentum parallel to the axis would be sum of all mr squared omegas. The sum of mr squareds is given a name. It's called moment of inertia. So angular momentum about the axis would be mr squared omega, where mr squared is the sum of all the mass into square of distance from the axis of all the particles. So we switched from definition of angular momentum of a particle to angular momentum of a system of particles, like in a rigid body rotating about an axis, and we are interested in angular momentum about the axis. If the mass is symmetrically distributed about the axis, the angular momentum components perpendicular to the axis cancel out, and angular momentum does not depend on the position of the point on the axis. And anyway, the angular momentum along the axis, about the axis, will remain sigma mr squared into omega, where sigma mr squared is our moment of inertia. Diagram shows a plane containing the z-axis, and at the instant shown, the linear momentum vector of the particle going around the circular path is directed perpendicular to the plane. The angular momentum of this particle about a point P on the axis is shown in yellow color, represented by PB. The length of the vector PB is mv root r squared plus h squared. Its component along the axis L cos theta is shown in green and is equal to mr squared omega. The component perpendicular to the axis shown in pink color is L sin theta and is equal to mvh. The components perpendicular to the axis cancel out if there is symmetry about the axis. Like imagine a disk rotating about its own axis. For every particle on one side of the axis, you can find another particle on the diametrically opposite side, and their components, their angular momentum components perpendicular to the axis cancel out. So for the rigid body like this, the angular momentum about the axis would be same for any point on the axis and can be got by simply summing up all mr squareds, and angular momentum would be mr squared omegas of all these particles. This sum of all mr squareds is called moment of inertia, and this depends on the geometry of the body and the axis. So do remember, angular momentum about the axis is independent of the position of the point on the axis, and if the body is having a mass distribution symmetric about the axis, the components perpendicular to the axis cancel out. Even if there is no symmetry, the components perpendicular to the axis will not cancel out, but the component parallel to the axis will be sum of all mr squareds into omega.